The Right Nothing, which is the name of my book, I wrote a few months ago.
Take it away.
Okay, everybody, my name is Michael Snyder, and I study magnetism, and I also, basically I study physics. And I'll have half my presentation on the ferrofluid cells that I work with. We have one in the back that's going to be here all weekend that you can check out. And I also will talk about vector space and some creative things I've done with it. Okay. Now these definitions, I've been working on this particular work, this ferrofluid cells since 2006, around 2006, 2007. And we started out with a Hill-Shaw cell that is basically two pieces of flat glass. It's optically flat. And then we have a drop or two of ferrofluid between the two pieces of glass. The ferrofluid is Fe3O4, which is in a 10 nanometer size particles, which is much smaller than the wavelengths of light that you'll see show up on the images. And sometimes I will say cell, sometimes I will say lens when I'm referring to the instruments that I make. Okay, this is early setup. I was still an undergrad at this time. And you'll see a 150 millimeter piece of glass, and of course the ferrofluid, another piece of glass right here. And then there's a magnet. And what I could do was I had a camera on the inside of the box, and I could just see the effect the magnet was having on the ferrofluid cell. And I'll see it in the picture up there and on the monitor, and literally just hit the button and take a picture. And this was, like I said, 2006. Okay, the apparatus is basically a piece of glass, round piece of glass, and we have LEDs around the perimeter. And here's some early work. 150 millimeters, which is 6 inches on the left-hand side, and slightly smaller on the right-hand side. And the one on the right-hand side has a hole cut out, which made it easier to work with certain images. Some early pictures. This is when we were using pretty weak LEDs, and we could only get background information, basically. And what we saw was like a halo, and it shows up anywhere where there's a magnetic pole. And I can't tell north from south just by looking at these pictures. But I can tell anywhere where there's a black area, that's a magnetic pole. And on the left-hand side, it's rotating on the y-axis, and the right-hand side is rotating on the z. Any questions so far?
Could you describe what ferrofluid is?
Ferrofluid is basically a medium, in this case it's light oil, and then there's very small particles in a 10 nanometer size, and the particles have a magnetic moment. So basically, anytime they get around another magnetic field, the particle has no choice but to align with the field. The catch-22 is the particles are so small, they should not affect optical light. You know, a laser pointer is 650 nanometers, and particles are 10 nanometers. So in theory, you should not have much of an effect. And if anybody uses the cell during this weekend, you'll have proof that you have an effect right in your hands.
Was this something that you discovered, or something someone turned you onto it, or?
I was an undergrad. I needed a final project, and there was a guy on the internet. I was on a physics forum. He said he could see the A field, and if y'all don't know, there's an magnetic A field and magnetic B field and so forth. But in theory, the magnetic A field can never be observed. So this guy was on the physics forum saying, hey, I can see this. And I said, well, send me one of those. And that was my final project for my undergrad. Okay, had I known, I probably would not have asked for the Sunday one, because I've been working on this for 5 years. Okay, so basically we have a magnet in the picture. It's a cube magnet, 1 inch cube. And you'll see the light from the different LEDs are warping around the magnet. And it's in real time. You literally can, as soon as you move it, we're looking at a pole. We can guess that's the North Pole. Of course, it's a 50-50 guess. North and south. And notice that you can see my fingertips. There's no distortion here. If we had optical distortion, then that would make my life so much easier. But basically, we have this light, this doing this light thing in the X and Y axis. Anything in the background just passes right through the cell. And these images, you could say they're magnetic contours. If you map the potential energy around a magnet and took the contour plot of the potential energy, you would get images like this, which is the reason the guy said you could see the field. Magnetic potential. Nearly everybody probably works with voltage, which is electrostatic potential. This is magnetic potential. Okay, so this is a 1 inch magnet. It's on its side. Of course, we have 2 poles. 3 magnets, north, and we're going to say the top is north, 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 bottom is south, 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 and see how the lines join together. The cell reacts to the whole field. It doesn't react to just one magnet. It's, basically every magnet is superpositioned over the other magnet and the other magnetic fields. Okay, there's one small change between this picture and this picture. The center magnet was flipped. So instead of north, 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 south, 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 we have north, south, north, south, north, south. So I explain this as like taking a spider web and flipping it. And we get these nodes where the field goes to 0. And let me clarify that. The potential energy, I might get myself in trouble, but I'll go ahead and try again. The area right here is where the north field's going one way, the south field's going the other, and you get an exact 0, a null point. But just because it's a 0 field net does not mean it's a 0 field gross. You can still have a whole lot of energy there, but it's just where they cancel each other out. Okay. Each LED produces each LED will produce either 1, 2, or 0 lines. An LED will never produce 3 lines, will never produce 4. A lot of times I will see pairs, 2 at a time. And each one will come in like, I'll have one line go to the left, I'll have one line go to the right, and they will go all through this complicated field. And when they get to the 0 point, they will twist around each other and go through the null point. Red always wraps around red, green always wraps around green. They never accidentally wrap around each other. So the main thing about this picture is that we have these 0 points, and we always have 2 lines going through them. Okay. This is probably 2008, 2009, and I have a ring magnet, and the ring magnet is coming up to the barefoot cell, and I'm getting a spirograph. I don't know why. I wish I did. If I could explain this, my career would be much better.
That's my next question.
I have a question. So, do any other, is it particle physics that this is directly the field that is involved, or?
It's condensed matter is the field it's in, but it falls between the cracks very well because there's people who can study condensed matter normally don't do magnetism. The people who do magnetism normally don't do condensed matter, and the people who do optics normally don't do magnetism. So this is just where like 5 disciplines come together, and each discipline's sitting there scratching their head, saying, "What's going on?"
Has it caught the attention of any other people wanting them to study it, or?
I have a business that sell these, and I sell 1 or 2 per month, and I have sent them to universities all around the world, Germany, just a few months ago, for example. So there's lots of people looking at this, but nobody's figured it out, or nobody's published a paper yet that says this is what this is. Okay. So that's a 2-inch ring magnet facing the camera. We have a spirograph. This is a close-up. Now remember, we had 2 lines going through the nodes. This is kind of similar. We'll have one line come in clockwise, one line come in counterclockwise, and they meet up. And they don't twist around each other, but literally I see 2 lines meeting on all these lines in the center. Okay. Of course, everybody knows this quote. Here is a cartoon of the magnetic moments of 8 magnets. And basically I'm just showing the arrows to the north. So that's north, and so forth. Okay, I can take this cartoon, this placement, and feed it into MATLAB and do a computational plot of what the field should look like. And here's a contour plot. And if we look from the top, this is the potential, I'll go ahead and say potential energy of these magnetic moments. So it's kind of like a frog. And the story I tell is, I'm working at 2 o'clock in the morning in the basement of a physics building, and my experiment's looking back at me. Okay. Oh, there's the real thing. So mathematically, we can go from these moments to these contours, which is not easy to compute, but you can compute it. Or we can just hold the cell up to the magnet and look. The good thing about being an experimentalist is you're always right. You don't know what you're right about, but I know this is good data. I just don't know what the data's answering. Okay, so that's up to last year. And then I did some more work, and I figured out that each line has its own polarization. What this is I used a polarized filter and took 12 steps, rotating the filter, and I would watch lines come and go, which is very surprising. I did not expect whole lines to come and go. And I would take 2 of those pictures and subtract them from each other, and what's left is giving us polarization information. Now the green means the line was present in both pictures, so the green is just for reference. But like this orange line here and this orange line here, I know from how I've done the subtraction that they have exactly the same polarization. And like this gray-blue line here and gray-blue line way over here. Anywhere to where any color other than green, if they're exactly the same color, then those lines have exactly the same polarization. And how to explain this? Normally polarization is a very easy thing to lose. You don't conserve polarization. Right? Any rough surface will mess it up. So if I have a whole line with the same polarization, that means either the line is creating the polarization, which might be, I think is unlikely, or the whole line is like a reflection. Not only just a reflection, but like a perfect reflection, because to have the same polarization, then the optical distance should be the same from the LED, and so forth. So I won't bore you with this, but I'm just saying each line having its own polarization is very surprising. Okay, and this is a similar picture, What happened was we had a ring magnet, and they're very brittle, and one broke one day. You know, if you're working in the dark and if you're not careful, they can jump out and bite you. So one of the ring magnets broke, and I went ahead and used it, and it produced this beautiful pattern, basically. And using the same polarization subtraction technique, I can tell every orange line here has the same polarization.
Excuse me.
Yes?
When you say polarization of these lines, could you explain that a little bit?
Yeah, I probably should have put a slide in there. When light moves, when a photon moves through space, it has an E field and an M field, an electrostatic field and magnetic field. And they're perpendicular to each other. So let's say this is the electric field and it's perpendicular to the ground. So that is one, as this moves, that is one polarization. And if you turn this vertically, and don't look at the lines on this right now, but that's for later. If we turn this vertically and say this is the E field, the plane of the E field, then this is a different polarization. Regular light has both. Regular light bouncing off any rough surface has both. To get polarization, your sunglasses, for example, is a very good example. It only lets light in that has a particular polarization. Does that answer your question?
I think so.
Okay, so basically the surprising thing is that, in fact, we'll use this as an example. See how this orange line kind of joins up with other lines, then separates? That means this polarization is the same before it goes through, and then when it separates, it's still the same. That means this surface cannot really be doing anything other than reflection. And not only is it reflection, but it's very good reflection. Now, why is something reflecting a lot of light at that point? I don't know. Let's see, I might have a few more slides that will help. Okay, this is the same process, but I put it to a loop, and you can see how these bunches of polarized lines run together. Oh, and just when things are getting fun, I got a bunch of these, by the way. Every time I think I figured it out, I get more information. Okay, now in this picture we have a magnet, and we have a standard picture. We can do this in the back table anytime we want to this weekend. And I took a flash, and basically this is the same picture, but I turned off the LEDs, took a flash at a 45-degree angle, and shot it, and took a picture of it. And I picked up two golden lines. I also picked up this blue circle. Now I think I know what this blue circle is. It showed up in my data before. Oh, excuse me. But the two golden lines are kind of unique and new to me. And notice how they are in the foreground. The blue circle runs underneath them. So the two golden lines there is what I'm interested in. Okay, very complicated picture. I only want to show you one thing about it. Okay, magnetic pole, two lines. So far, so good? Same thing, using a flash, but in this case I'm using a flash and I'm also doing the polarization subtraction technique that I do. So this is a very complicated picture. It's showing polarization and it's showing flash. Okay, see that little pole right here? I don't know if it's north or south, but there's a pole right there. Now look in this picture, there's two lines. Pole right there, two lines. Pole there, two lines. This presentation is brought to you by the number 2 because it keeps showing up. And this pattern, right here is the null point, where the field goes to 0. How do the lines know where that point is? I literally would have to run a GPU card for 10 or 15 minutes to figure out exactly what this image looks like when you do a computational analysis. Yet these lines find it exactly every time, and they find them in real time. If you move this magnet, these lines will move with you, and they'll still be correct. You look like you had a question. Okay. Okay, so brought to you by the number 2. We still have 2 new lines there. And this is the final picture of this first part. Very complicated field. Turn on the flash, my 2 lines show up everywhere. And note, there's a pole, there's the 2 lines, there's a pole, there's the 2 lines. And that's the present state of my research. My research isn't funded right now. I'm running a business that makes these, so there's kind of conflict of interest right there. But I've had lots of people interested in it, lots of nibbles, but no funding. But so this is as far as I've gotten. Okay, now we're going to talk about difference in the topic.
Can I ask a question?
Sure.
Is the quality of the light from a flash a lot different, or a different wavelength, or something from an LED? Is that why the 2 lines show up? What's the difference?
There's many differences. The LED has a certain frequency that the light's at. A flash covers all frequencies. An LED can have some polarization selection. It can have a little bit more polarization in one direction than another. A flash will always be random. The fact that I'm getting golden lines means the light must be interacting with the magnetic fluid. Otherwise, they would be white. So white light goes in, and golden light comes back. Any other questions?
It's almost similar to solar flares, and so the arcs on the solar flare.
Yes, that's been brought up many times, and I completely agree, especially when you get images like this. If you do the analysis, the contour lines look like this. But the amazing thing is, you just hold it right up and you can see it. So,
but you're saying this is a mysterious force that you're seeing in these gold lines?
Let me be clear. There's nothing mysterious. Everything here we understand parts of. We just don't know what the whole picture is. Any particular effect, you probably could find a page in the textbook that would talk about it. But when you put all these effects together, we're missing a chapter, basically, in the textbook, as far as I can figure out.
Is the chapter that explains why it interacts with light and shouldn't interact?
It would be nanoscale magnetism. It would be nanoscale optical magnetism is the missing chapter. And it's just because there's nothing to study. Nobody studied it 100 years ago. We didn't have it. We've had this since 2005. So I'm sure somebody will figure it out.
It almost seems to me like you're getting into the where people start talking about the frequencies of the visual light and everyday experiences that we have. It's like you're sort of starting to hack into that.
Oh yeah, this is
programming a little bit of the visual light.
Yeah. I don't know if I said it when I started, but I'm considered a hacker of other physicists. I'm hacking physics. Okay, speaking of hacking physics, let me go to the next section. Okay, so my business is not going so great, it's doing okay. And a whole lot of pressure was on me a few months ago. And I kind of went crazy. And I don't mean lock me up in the hospital crazy, but I just had enough of it. And I started studying something new. And this happened because I found a few physical constants. Physical constants is something physicists love, speed of light or Planck's constant. There's a whole list of them. And there's physicists that all they do is they study the relationship between the constants. And I started doing that. And every time, and I'm not the first, but every time I looked at one constant, I could find a connection to another constant. And I spent about 2 months mapping that out. My background before I was a physicist was with networking. Imagine diagramming a network. I think everybody in the room can diagram a network, or at least visualize one. I started mapping physical constants the same way that you would map a network. Okay, and that's what we're going to talk about. Okay, so we have XYZ Cartesian space. This could be called a vector space. We good so far? Okay, I'm going to make a new vector space. And instead of XYZ, I'm going to make it lion, tigers, and bears, oh my, where oh my is the origin. Can I make this vector space? Is this legal?
Yes.
Yes. You can make any vector space. Basically, a vector space is where vectors live. We're used to 3D, but if you do any kind of statistical mechanics, you can work in very high numbers of dimensions. But it's just a big vector space. Okay, so this is a tame example, a lion, tiger, and bear. And yes, I can do this. But then I did something else. The lion, tiger, bear is the normal example. Here's what the abnormal example is. I said, let there be a vector space of the speed of light times the Planck constant, times the Ampere constant, times the gas constant, times Wing's displacement constant, times the universal gravity constant, times Avogadro's number, times the Faraday constant. And I said, let their space let it exist. And it does. And that's a great thing about mathematics, is there is a creative part to it. Okay. Now, any questions so far? Okay. What should I say with this? Oh, the reason I picked these particular ones was because I said when I started looking at the physical constants like a network node map, these are the ones that came up over and over again. Okay, so, and if you'll bear with me, I'll have a look. I have about 5 slides of math, but as soon as we get through those 5 slides, and that's the rest of the math I got. Okay, on the left-hand side, we have a constant. Speed of light, Planck constant, and so forth. On the right, on the top row, we have mole, Kelvin, kilogram, meter, second, and ampere. So what I'm doing is I'm just displaying, the speed of light is meters per second. And you can just look across the row, and there's meter per second. These are exponents. So c raised to the first power is on the top, meter raised to the first power is on the top, second raised to the negative 1 power is on the bottom. So this is a matrix, basically. And what I want to do is this is 8-dimensional space, basically. Oh, I'm using the word too much. But where the CH and AR, this vector, this column, is 8 dimensions. And this row here is 6 dimensions. And I can show this. Imagine I take 8-dimensional space and I squish it to 2 dimensions. And then I take 6-dimensional space and I squish it to 2D. And that's legal. You can always project a higher dimension into the lower dimension. We do it all the time. We have 2D graphics, but we live in a 3D world. So you can always go down in dimensions. So I took 8 dimensions, squished it to 2. I took 6 dimensions, squished it to 2. Now, the 8 dimensions, I need to introduce a concept here, are units, or orthonormal. That means they're perpendicular to each other. They share no points in common. There's many definitions for orthonormal, but that's the standard. When we say Cartesian space, we mean an orthonormal Cartesian space with x, y, and z unit vectors. Okay, these constants, see how they mix and match? There's part of it is a mole, part of it is a Kelvin, part of it is a kilogram. That's not orthonormal. These axes are sharing, the moles and meters and stuff are straight lines. The constants that share more than one attribute are curved lines or they're just not straight lines, and that's what I'm going to show. Okay, so we'll let this be the 2D space that's orthonormal, that came from the 6 dimensions. And we'll let this be the 2D space that's not orthonormal, that came from 8 dimensions. And we'll notice how the lines cross. And what I really want to know is where these two spaces intersect. It looks like a very simple problem. The only real reason we can't solve things like this by equations is because we don't know ahead of time where these nodes are. So, this line crosses here, this line crosses here, this line crosses here. So basically, I can translate from one set of space to another set of space. I can go from an non-orthonormal space to an orthonormal space just by using this transformation. Any questions? Okay. Mathematically, what I'm describing is pretty tame, and people do this stuff all the time. They just don't do it with these constants. Okay. So, here's one example. Okay, I want all these columns to go to 0. So basically, this is a matrix. And there's some multiplier that when I multiply it by C and then add the whole thing up, we get 0, 0, 0, 0, 0 all the way across. In this case, 6, 0, minus 2, minus 1, minus 1, minus 1, minus 1, and 2 fulfill this requirement. Now notice this is not the only way of doing this. There's many, 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 many other combinations. And there's no easy way of finding them. You can't really go backwards in this process because you're adding up to the 0, and 0 is, in this sense, is not unique. So we have a process that works fine in one direction, doesn't work very well in all the other direction. And how I solved this was I tried every possibility. I'm grinning because they say that you cannot solve a problem on 8 axes. And what I did was basically I just used PhreakNIC loops and took every possibility from minus 700 to 700 on my first parameter, my second parameter, my third parameter, and I recorded every answer that worked. And ended up with like 35,000 of these equations that would work, that would produce a 0. And what people said was, I was looking at, I found noise, that this was random. And they said it was trivial, too, because anybody can do this. Well, my response is, if anybody could do this, why didn't they do it before? So I have 35,000 equations. All of them produce 0 in this bottom line. When I plot it, I don't have random data. I have highly periodic data. This is, anybody who's ever used an oscilloscope could recognize something like this. So we have 8 inputs, triangle waves, and so forth. Okay, so hold this thought. We're nearly to the end here, but hold this thought, and I'm going to introduce a second thought. Okay, not only can I solve for 0, but I can solve for other things. For example, an ohm is defined as a kilogram times meter squared divided by second cubed divided by acre squared. This is a standard, if you look into Wikipedia, this comes right up. That's the definition for an ohm. So my program can try every possibility that equals an ohm. And that also generated a long list. Now the one shown here, Planck constant to the first power, Avogadro's number to the second power, Faraday's constant to the inverse square power. Okay. Using this, let me wrap all this together. Using this technique of finding certain units through my transformation matrix, which looks really simple after you solve it, but if you don't, it was very hard to solve it the first time. I can get different units expressed as physical constants. For example, if you do speed of light cubed times Avogadro's number divided by Faraday's constant times gravity, you will have exactly the same units as a Tesla. And so forth. Down here, this is the one we were looking at. H to Avogadro's number squared over Faraday's number squared is an ohm. So, I've been doing physics for over 10 years, and I've never seen anybody write these in this form. But, on the other hand, they self-prove themselves. Using the unit analysis, anybody can check these. The top number, now let's do another one. Newton. I did not know until the program came up with the answer that you can write a Newton as the speed of light to the fourth over g. It has exactly the same units as a Newton. And the number underneath it is just the value at the top, this numeric value. So the top is the units, which is a Newton. The bottom is the value. You divide it by the value, you get 1 Newton. So every one of these, and I call them nodes, every one of these nodes are something that's very easy to check. Okay, and here's the finish line. Now the Faraday constant can be written, let me tell you the story. So I did all this work, I sent it in to a bunch of journals, and I got the thumbs down at every journal. It's too simple, it's too trivial. And these are the same people who researched pi to 15 million digits, and they're saying this is too trivial. Okay. No physical interpretation was another one. And this is kind of important. Yes, I can create a lion, tiger, bear vector space, but is there a physical interpretation to that vector space? That's important to physicists. I think everybody can understand this, that you can create something that there might not be a physical interpretation. So forth, so good. Okay. So the other question was, is there a physical interpretation? And I pointed out that quantum mechanics has a load of things that don't have physical interpretations. Literally in quantum mechanics, you may have 25 steps. Step 1 has a physical interpretation. Step 36 has, or I added a few. Step 25 has a physical interpretation, and everything between the two don't make sense. You couldn't figure out in 1,000 years what the equation's actually doing. In a sense, 2 plus 2 equals 4. Well, when you start doing quantum mechanics, you don't necessarily get 4. Okay, so the physical interpretation was one of the questions. And the third thing was, there's no way to tie my work to first principles. No, you can think of a tree of knowledge. And the physicists, including me, love anything that we can track from the ground up. We know where it starts and we know where it ends. It's from first principles. And my work is not from first principles. What I did was basically, I said, well, there's a leaf, 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 there's a leaf. They must go back to the trunk of the tree, somehow, the tree of knowledge. But how that leaves are connected to first principles, I don't know. But then I got a clue here. Okay, so the Faraday constant is elementary charge times Avogadro's number. And I'm not sure I can say this man's name correctly, but I'll try. Von Klingsing. Anybody know how to say this name? Klingsing. Constant. This is a very important constant in condensed matter, of all things. I just thought of that. And in solid state, it's used in very high-end electronics, experiments and so forth. So it's defined as Planck constant over elementary charge squared. And look what my computer found. My computer found h times n squared over f, but when you break this down, you get h over elementary charge squared. So my computer found the von Klingsing constant as just one of these nodes. And if you don't, this gentleman received, now he did a lot more work than just this constant, but he received the Nobel Prize in 1985. And it's basically because of this value and how it shows up as integers in solid state. So my conjecture is that I found all these relationships that have to be true, that they prove themselves. And one of them is well known. So if this one's well known, maybe the other ones can be linked to first principles also. Basically, the argument is where there's smoke, there's fire. And we definitely have smoke here. Okay, so long story short, just bear with me for a second. Okay, remember I had 35,000 equations. There's a command on MATLAB called lowest echelon form, reduced echelon form. And when you run reduced echelon form on those 35,000 equations, you get exactly 2 equations. Now, the chances of that, my program was not picky. It took anything that made this true. Right here, the sum 0, 0, 0, 0. It had no preferences. The chances of having 35,000 equations drop to 2 is very low. That means there's some unifying force there, or some what am I trying to say? It was a surprising result. I took that result and I published it. And this paper was published a few days ago. And this DOI number here can be Googled on the internet. You can read my work. So my first paper was dealing with these 2 equations. And my second paper is dealing with all these nodes, these relationships. And it's under review, and I expect that to be published. I'm hoping it will be published next month. And that's it. Yes.
I have a suggestion. If the journals want to ignore you and not publish this, I would just go ahead and use it and build the time machine and go back to Sir Isaac Newton and present it to him and see if he thinks it's valuable.
I second that thought. I'm not sure I can build a time machine, but I think that's a good idea.
I was curious about the visual, how you created this visual map. Just like I think they used the visual map to guess the next primes.
Right.
Can you predict? I'm interested in that field where you're taking.
I can share a few secrets for what I found. This is basically kind of an encryption problem. It's an oversubscribed or undersubscribed. I don't know what these multipliers are. And I have this matrix. Now, this matrix could be much larger than this. I just picked a smaller matrix because it worked for me. But mathematically, what I'm doing was, they say this would grow at n to the 8th or O to the 8th. Does everybody know what I say when I say O to the 8th for a mathematical or for computer scaling? Computers, certain problems scale at different levels. And if you're working on something in 3D, most of the time that scales in O to the 3. If you're working on quantum mechanics, it can scale to like O to the 18, which means you can solve one problem in 1 minute, and you can solve 1,000 problems in 20 years. I may not have said that right, but basically, the harder you make the problem, it takes a much longer time to solve it. And how I solved my problem was, I did not do the whole matrix. I started out doing the whole matrix, this multiplication, try 1, 1, 1, 1, 1, 1, see if the answer is correct. Try 1, 1, 1, 1, 1, 2, see if the answer is correct, and so forth. And originally I did the whole matrix, and it was taking forever. What I figured out was I could just do one row at a time. If I do ampere, and the answer is not 0, then why do the rest of the matrix? So I fixed my scaling problem by doing test runs on this matrix before I did a full matrix multiplication. If any column came out to non-zero, there was no reason to do the rest of the matrix, which saved a lot of time. In this case, now my problem's still growing at O to the 8th, but then I'm only checking one column. So that's 1/6 times O to the 8th, which is much quicker than 1 times O to the 8th on scaling. Other questions?
The graph you had that had the colors to it, how are the colors being assigned?
In this particular one?
Yes.
In MATLAB, when I do this, basically I just feed my data, my matrix to MATLAB, and it picked a random color for each one. In my paper, I have it labeled.
Can you tell me, like, if the colors represent anything?
No, in this case, each color is just an exponent. Exponent 3 in this example, exponent 4 in that example, exponent 5, and it ends up being like a blue line going somewhere. Now, in my paper, I actually have all that labeled. Any other questions?
Is there any significance to the symmetry of that particular picture right there?
I'm smiling because I had some very important people telling me I was looking at random data. And I sent them an email back. And I said, will you call this random? Any other questions? Okay, I want to thank you for being my audience and sticking through this.